and in our new people as well. We are delighted to have you with us. And if you're not on our email list, please make sure you sign the list over on the table there. And we only send about 2 emails a month, so let's cause problems there. But yeah, we're welcome everyone. Let me give you, I just did about 10 of these. If you need one, let me know and I can send you one. These are star maps. Um, and we are really happy to have at our meeting two of our previous speakers, Alan Stern, wave, okay, and Leslie Young. And Leslie, I think, is going to be our next speaker on March 7th. So that would be, I think, 7 weeks from today, and or 6, maybe, March 7th. Yeah. Anyway, we'll be sending out notices on that. And just want to say that we're honored to have Bob Grimm here. He's one of our locals, and he's given what is this, Bob? Your fourth or fifth or sixth talk? Somewhere, maybe something like that. So I think a lot of you know him, but maybe Bob, you can say a few words when you start about your background, and of course your talk. Yeah, well, yeah, if you got the Mountain Messenger and maybe our first email, I think it was my fault. I like to blame my husband Lennon, but because he read it, he's my editor. But yeah, we called him an astrophysicist instead of a geophysicist. So, anyway, so welcome all of you, and bathrooms are in the back if you don't know the hall, and yeah,
That's part of the rec.
what?
That's part of the rec.
Oh, yes, and thank you to we're Skywatchers is under the Coal Creek Canyon Parks and Rec, and they're our sponsor, and we always like to thank them. And thank you to the Mount Messenger, our editor there has always been really good about giving me an extra day or two when I needed to write my article to them. So Bob. And so Bob gives this talk, and then Monday will do about 15 minutes or so of updates. He always does international space missions updates, so he will be after Bob.
Okay, you didn't quite finish all the troubleshooting.
Yeah,
Do we?
you can get rid of that thing at the
Yeah,
top.
I don't know how to do that. It just went away by itself before. So look, hide floating meeting controls. Oh, look at that.
Oh, perfect.
Okay. Okay. So yeah, I'm a geophysicist. I started off as a planetary scientist. I'm in industry for several years. When I was in industry, I realized that things we were doing there would be great for planetary science. So I came back to planetary science, and that was 20 something years ago. A lot of people to thank, people in the science team for this, NASA for supporting it, the people who built it at Goddard, and a company called Heliospace in California, Southwest Research, and then Firefly Aerospace built the spacecraft. And since Alan's here, I'd like to thank him for hiring me 23 years ago, because that's why I'm doing this.
It's a good thing I said no.
Yeah,
saying no.
that's its own story, isn't it? This, I don't know what I'm doing here. So I'm gonna go back to this. Okay, so NASA does this thing called CLPS, Commercial Lunar Payload Services. It's a busy slide because there's a lot of moons happening. NASA's going back to the moon with astronauts. I think they rolled out the Artemis 2 today. But there's a big robotic precursor and parallel program, and they want to do 2 missions a year. And there's a couple of monikers that go with this that turn out to be not so good. One is FedEx to the moon. The idea is you would just propose your payloads and both them on the spacecraft and get your data back from the moon. Supposed to be, really fast and easy. And that turned out not to be true. And then there's this expression coined by the same person, more shots on goal, with the idea that it's a hockey analog. But there's been 4 shots on goal, and only one of them has worked. So the moon's a pretty damn good goalie so far. So I'm not so sure that's a good expression either. So these are just payloads that our company, Southwest Research, has. LMS is what I'll talk about today. I've got a second payload that was selected in 2021 for a 2027 flight, also doing geophysical things. The biggest one we have going to date is called Dimple. It's a rover, and it grabs samples and will actually figure out how old these volcanic, the very young volcanism we think on the moon is. So a lot going on, and leading into astronauts and future opportunities. So the moon is happening. Let's talk about the history of the moon. The moon is pretty well established that it was formed by what they call the giant impact. It's something about the size of Mars. There was maybe a dozen objects of this size that were floating around after the planets formed. One of them collided with the Earth, and the bits, most of it merged with the Earth, but the parts that were left in orbit formed the moon. The initial moon would have been very hot, probably completely molten, and it's called the magma ocean. The entire world was just, a giant puddle of lava, and it eventually cooled and solidified, and crystals sank to the bottom, and eventually you're kind of squeezing down the part that's left, the part that's crystallized. There's a crust is formed, and there's this little bit left. Finally, there's this brown stuff at the top, which is called, one of the 2 words you have to learn tonight, creep. Okay, so creep is a very common word among lunar petrologists. So it stands for potassium, rare earth elements, and phosphorus. These are all what's called incompatible elements. They don't fit into crystal structures. So when a magma is crystallizing, they're always left out, always left out, always left out. So at the very end, they're just the dregs that form at the very end. And this is thought to be sandwiched between the crust and the upper mantle of the moon. These are also important because things like thorium, uranium, potassium are all heat-producing radioactive elements. So even though the bulk of the mantle of the moon has radioactive elements in it like the Earth does, there may be this kind of liquor of highly radioactive stuff that's sandwiched below the crust. And where it is and how much of it is unknown. All right, so the moon's pretty familiar, the near side at least. It's got the dark parts and the light parts. The dark parts are called maria, that's Latin for seas, and those, it's basically all basaltic lava. So basalt is the most common volcanic rock in the solar system. It's sort of the most common on Earth. It forms all of the seafloor. Basalt is the first rock you get when you melt a silicate planetary interior. It's the first stuff that squirts out, has this composition. And around here, we know that it's the Table Mountains in Golden have the basalt caps. And so it's right here too. The rest of the moon is the early primitive crust. It's mostly made out of a mineral called anorthite, which we have in some of our granites around here. But it's a very light silica-rich rock. The only other thing on here is this whole western near side of the moon is called ocean of storms, Oceanus Procellarum, and this word Procellarum as a name place will come up as well. I just click here, is that gonna work? No. Okay, so we look at the moon, we see the man in the moon. That's what my talk is about. And so, yeah, that's the middle one's kind of, what you might imagine. The other one is from the famous, early film about the Jules Verne story. Here's some various cultures around the world where people see the Chinese see a rabbit in the moon. I don't know who sees Wilma Flintstone, but that's what that looks like at the bottom to me. So why is there a man in the moon? That's our question. The whole sort of why is it that this basaltic volcanism is mostly concentrated on the western near side of the moon? You saw there was hardly any dark spots on the far side, and on the near side, it's mostly on the western half. So why is that? So it's not just that it's all the lava's over there. It's also rich in thorium, and other incompatible elements. This is a satellite map of the surface distribution of thorium, and it's a big blob that's basically over top of the Western Maria. And so because that's in this area, Okeanos Procellarum, this has been called the Procellarum Creek Terrain, PKT, and it's a shorthand I'll use for this anomalous region of the moon. And so the question then is there a genetic relationship between these two? Did excess heat-producing elements that were sandwiched in the mantle below the crust on this western near side, is that what caused the volcanism? Seems like a good hypothesis. So right after this was discovered and named, this is well after Apollo that they figured out this thorium. And some of the first papers were around 2000. And this one guy, Mark Resort, was a graduate student with my postdoc advisor. They moved on by then. But he wrote this paper as part of the last chapter of his thesis, where he said, suppose we have a thick layer of this creep stuff below the Western Maria. I'm going to do a computer model of the heating and show how hot it would get. And in fact, it gets like really hot, and it gets hot enough to melt, and it gets hot enough to stay melt, to keep most of the moon molten, at least in that little area, for billions of years. So I reproduced that model in 2013. That's what's kind of shown on the left. So the PKT would be at the top here, and that's kind of the hot part. But it turns out that didn't match other observations, gravity and topography, things that geophysicists look at. If you had that much hot stuff, it would be buoyant. It would stand up really high. That's what Earth's mid-ocean ridges do. They're hot, they form ridges. So why isn't this a giant ridge? So I took the same amount of radioactive material, but I put it in the crust, and you don't get the high topography. You don't, but you don't get long-lived volcanism either. You can't keep the deep inside hot enough to sustain the volcanism. So if this thing on the right is correct, something else has to have caused the volcanism. And this makes very clear predictions that, between looking at from the top to the limb, we should see many hundreds of degrees temperature difference if that model is right, but just tens of degrees if the other model is right. Mm-hmm. So all the Apollo missions landed basically in the PKT. And nobody ever said, well, we think it's really hot under there. So maybe we're biased in some way. Maybe we need to go outside of PKT and compare back to it. So we can say, okay, is the part that's blue really blue compared to the red? And so one way to do that is to go, I can just kind of pull it towards me, is to land outside of PKT. And a good place for that is this other Maria, this little isolated one that's called Mare Crisium. So this was from our proposal in 2018, and we suggested that this would be a great place to do this experiment because you can kind of look back into the middle of the PKT and kind of trace your line past some of the Apollo stations where there's data. And wouldn't that be great? And so when we got selected with this meeting, and there was another experiment that was doing heat flow, and I talked to them, I said, hey, wouldn't this be good? And we worked together, and they said, yeah, we'd like that location too. We went back to NASA. And the other payloads that were selected with us were either going to go to the South Pole, a whole bunch of them, like, we're going to the South Pole. And nobody else cared because they had other experiments that just didn't really matter where they were on the moon. So we got to direct basically the mission to go to Mare Crisium. And NASA worked with us to actually pick the exact site. So Mare Crisium, I can point to you guys. I can't point to Zoom. So yes, here's Mare Crisium on the limb. Here's a blow up of it. It's several hundred miles across. We wanted to land away from these magnetic anomalies. We didn't want them to mess up our experiment. And as we zoomed in, we kind of identified this area as being kind of flat lava, has these cool couple of volcanic cones in the middle. This one that we called the horseshoe, this one we called the taco. And we're working with NASA to get closer to it. And eventually, they picked a handful of spots that were clear at the local scale, didn't have very many craters, didn't have very many rocks. And I think it was out here, it was the final site. So this horseshoe feature here, you can kind of fit Stanley Lake kind of right in the middle right there. So it's not very big. I also submitted a name to the IAU, the International Astronomical Union, of Mons Lettre. This guy, Pierre Latreille, was a ornithologist in the 1700s, and he named a lot of fireflies. And so the name of the company that was flying there was Firefly. So it was kind of a secret backhand compliment. So good thing they didn't crash and leave their scattered junk all next to our mountain. So all right, so here's one technical slide. This is the experiment that we did, involves electromagnetic. So you can use electromagnetic fields to probe the inside of the planet. And that works by there's some natural field, or you can take a transmitter. We use natural fields. That field changes with time. That field causes electric currents to flow in the ground, depending on how electrically conductive it is. And those electric currents in the ground make other magnetic fields and electric fields that you can measure at the surface. So we're able to probe into the inside, and we break it down as a function of frequency, just like your stereo equalizer or whatever. And so the lower frequencies go deeper. And so from a natural spectrum, we can reconstruct a profile of electrical conductivity versus depth. And that depends on temperature and composition, but it mostly depends on temperature. And that's what we'll exploit later. So we're gonna make measurements, some kind of magic measurements at the surface that tell us electrical conductivity. That's gonna tell us temperature. Okay, so this is what we selected was the magnetotelluric method. That's your other. What was the first word? Anybody remember it? Urcrete. Right, very good. Okay, the second word is magnetotelluric. Magnet, telluric refers to electric currents. So this is measuring electric and magnetic fields. Ways it's done on Earth is you have a magnetometer that measures the magnetic fields. Here, that's with these long tubes. We don't have to do that for the moon. But you have to measure the electric field. You do that, it's a voltmeter. So you basically have to have probes, and we measure it as a vector. So we go this way and this way. And what you have to do is bury these on the Earth, and it's very time consuming. And some geophysicists like it and some don't. And our company, when I started at Blackhawk, our boss, kind of gave me the geophysics birds and the bees talk about what they do. And he goes, we do not measure the electric field. It's like, it's too much can go wrong with it. We do these other things. So I thought, great. And then I went off and did this. I wrote a proposal to do this. So this was 1997. And I got my first grant to start building a planetary relevant system to make these measurements. And we made progress, but we were using the wrong sensor. And in retrospect, it was pretty naive, but it got me started. I teamed up with a space physicist and measurement person in California. We developed some concepts. We did some field tests. We were really interested in Mars to find water at that time. But then in the mid-teens, we got funded to build a prototype to go to Europa and try to look in the ice for water there. And so some of the elements that we ended up using, you can recognize here. You'll see in later slides. These launch the voltage probes, and this is this mast that carries the magnetometer. So when we wrote this proposal for CLIPS, this is the first opportunity for outside of NASA organizations to send stuff to the moon. And that's what our proposal looked like. So we're just going to use 3 of these electrodes. We'd use one common reference and then measure 2 out here. And the whole thing, we wanted to be a shoebox, right? This is FedEx to the moon. It's got to be compact. And so rather than do a boom with the way usually people do magnetometers, you want to get it away from the spacecraft so that you don't get interference. My colleagues devised this mast, which is really cool. It's got these coiled metal tubes that just shoots it right up. I'll show you how it worked. But this was our proposal. And it's not too different than what we built. So this is the flight instrument. The magnetometer is on the left. That's the little white thing. The mast is the big assembly over it. That's our electronics box. And there's these 4 electrodes that get shot out by springs. And they got red safety caps on them that get taken off. But you can see on this mock-up of the lander, there's our magnetometer at the top. And then here's 3 of the 4 electrodes on one side pointing in orthogonal directions. And the 4th one's on the back.
And what's the scale?
The lander's 2 meters tall. The assembly for the mast is like this. The electrodes are like that. couple of interesting points. The magnetometer's got very small. So this actual sensor, is only about that big. The new and novel thing was these voltage probes. People do this in space physics experiments all the time, but they're on very long, rigid booms. The spacecraft spins and everything behaves really well. We have to get these things out on our own. That's what this launching idea came from. And it has this very, very thin wire that was really hard to build. It's a multi-conductor cable, coax, and that got built and it all worked. But how would you wind it? How do you load it? How do how does all this work? Well, it turns out that they used an actual yarn winding machine. And the apocryphal story is one of the engineers was visiting his grandmother and she had this thing and he's like, that's what we have to do. So they experimented with like the pitch angle of the winding and how dense it would be and evolved something with 3D printing and tested it that worked out. Okay, so here's the obligatory, picture of the lander being assembled. There's our delivery team from Southwest and Firefly. If you look closely, you can see our stuff is on here. The electrodes are there. The mast is up there, and then they sent it off to the Cape. So we went to the launch. At first, I wasn't going to go to the launch, like it's just a Falcon 9 launch. It was awesome, so I'm glad I went. And it was a perfect launch. The orbit didn't go straight to the moon. You can get to the moon as little as 3 days, but they basically were in kind of a long looping orbit. In case they did not make that first opportunity, they would just keep orbiting until the moon came into the right position and then go to it. And that's in fact what happened. So they got off right away. So we spent 45 days kind of looping around. It got to the moon. This is the transit. You can see here's one of our electrodes right there. There's another one. We're gonna see a lot of views off of this side of the lander. This is our little ops room at Southwest Research Institute. So there was just a handful of people that were involved in this. We ended up not even running 24-hour shifts, right? We just woke somebody up if something happened. But the landing was exciting, but pretty calm. I mean, it went off flawlessly. The only thing that was out of the ordinary is that one of the lander footpads was not actually touching the ground, but that didn't seem to matter. Does anybody see what I did with my water? Yeah, maybe I'll lift it back. Oh, there it is, right on the edge of the table right there. Yeah, thanks, Terry. Okay.
By the way, I think the clicker should look for you.
Okay. So let me rather than try to do all these thank you, Dewey, in PowerPoint, I was gonna just put this on top of it. Yeah, okay. So you probably saw this stuff back in March. So this was one of the views of the landing, probably the most spectacular, where you see the shadow approaching the ground.
That's so cool.
You see the lander is going to settle. Nobody's explained to me what that thing that got shot off was. They keep saying it's a rock, but everything looks the same in vacuum, right? It could have been a piece of the insulation of the lander or something, and it would look the same. We had to wait about a day before we could deploy our sensors. This was the highlight of the mission for us watching this. So that's one of the probes being ejected. They were all 4 went off okay. Let's do that again. You can also see the wire being pulled out over here on the right. So that went 23 meters. And then lastly, we had our mast. So this is these very tightly coiled tubes that when you just release it, it just goes right out. So all that came off very well. Just recently, Firefly released a bunch of pictures from the mission that weren't available. Oops. before. Let's see, that I want to get rid of. This I want to go full screen. Nope. There it is. Okay, so this is right after dawn. And so the sun's from the left, and we're looking at that same view. So yeah, our electrodes are here, here, and then over there. Yeah, I'm still not clicking here. Yeah. Okay, so they had to vent the propellant tanks for safety. So, there's this weird stuff growing out of the spacecraft, ice, it looks like kind of popcorn. They also changed the surface, maybe Leslie can tell us why it looks green. I don't know if that's real or not. But definitely as time goes on, they're busy. Well, we don't even know any of this is going on. So yeah, you can see the ice changing, coming, going. And then the difference between here and the next one, there's our electrode, and then it's gone, it's deployed. And then the one here went, and there's one over here. So now you're looking, the sun's a little higher. There's the actual cable going out. This is the shadow. And things are still changing on the ground. And then you can see that our cable has moved. So there's so much stuff, there's venting so much propellant that they've made a little windstorm and pushed our cable over. You can see little marks on the ground where it's been jumping around. There's another piece of ice that comes and goes. And then this last picture, look at the difference there. We've completely jumped over this rock. Okay, and all kinds of these chatter. You can see how much the cable's been moving. All these chatter marks. And look, they've just blown off all the fines from the surface. So I don't think this really affected anybody's experiment, but it's one of those things that we didn't really know that this was happening until after the fact. So there was sort of some uh, partitioning, right, between the spacecraft teams and the payload teams and the actual spacecraft. We didn't really know a lot of what was going on during the mission. Yeah,
What
John.
was the propellant that was freezing and
I don't know. I might have known at one point. Okay, so we're here. So we're back. Okay, that's good. So okay, there's the lander on the surface. I have a little 3D model that's should be pretty accurate. It was mostly to show where our electrodes went. So we had to like look at a bunch of pictures and find everything. Okay, now I'm not announcing. Now I'm going to make something all. There we are. Okay, so we have a topographic model of the site. This is a view shed, so things we should be able to see and not see from the lander. So the launcher that you saw went to the west over that crater. The one to the other side went straight into another crater, and we couldn't see it. We have to kind of guess where it is. The one to the north, we should be able to see it. We think we see it, but the camera lens was smudged, like right where we had to look. And then the one to the south, we thought we had lost, but or just couldn't see it. But when the sun angle changed, we were able to find it sitting on the other side of the crater. So we need to know where they are because we need to figure out that's how we have to make the electric field measurement. So here we are during mission ops. Again, this was a busy time where I took these pictures. Not everybody was there all the time. I celebrated a birthday during this mission, and my friend Jody made me this awesome cake, which you can see the Blue Ghost lander with the licorice legs. So that was very cool. And there was an eclipse, so it was a lunar eclipse on the Earth. That makes it a solar eclipse on the moon. And so that was observed. And then we went up to sunset, and we turned off our instrument before total darkness. It was already starting to not perform. So we just kind of watched the sunset. Here's our last data screen, and that's Reef Nolan, the systems engineer, project manager, and we're having a beer there after we turned the instrument off. And John took this picture within a day, less than a day of when they actually ended the mission. Yeah. So you mark Chrissy in the little spot in the upper right hand corner, and night is just falling at the landing site. Okay, so this is how our data acquisition went throughout the mission, and I just want to mostly use it as for narrative. We had a high data rate and a low data rate because of restrictions. We were going to alternate back and forth with the what you see at the beginning and end of the mission, but in a move that kind of broke the Eclipse mold, where we didn't have much communication. We were supposed to like follow our script. Nothing was supposed to change. NASA said, "Hey, Firefly's willing to give you a lot more data. They have a lot more capability. Would you like to take your high rate data all the time?" Great. So we have these big chunks of high rate data, which really helped out a lot. The graph in the background is the temperature of our electronics box. So you see, we landed in the morning, right after dawn, and it got hotter and hotter and hotter. Eventually, on March 6th, it got over 50 degrees. Now, 50 degrees is not especially hot for electronics, but somehow, lost in the depths of time, that's all we tested to in TVAC. Because we were told by the lander it's never going to get hotter than that, and it did get hotter than that. So it's getting hotter. We're like, we should just turn it off and be safe. So we turned it off. That's why there's no data there. There's a little glitch right there where one of the guys, David, got up in the middle of the night, turned it back on, and it started to get hot again. We turned it off. Okay. So then I got like the most useful email I ever have in my life. It was from the Goddard engineers. He's like, "It's going to be fine. This is a once in a lifetime opportunity. Turn it back on." And it's like, okay. So we did, and it was fine. And it went until after local noon, at which point the lander overheated and they shut everybody off. So we were off for a couple of times. So people have started calling this afternoon period of inactivity the siesta. So we're going to call our time off in the morning the morning nap. So there's these two data gaps that we have, but that's part in the middle. It turns out to be really great. That's where the heart of our data is, because we had this awesome high rate data. We're in a very dynamic, active part of the solar wind, and where it starts to transition to the magnetopause, and so it's very active, strong data. And our electrodes, did I tell you they only work in daylight? Yeah, they only work in daylight because they couple to the sun sends off photoelectrons that couples to the plasma, and that's how we measure electric fields. So only when they're well illuminated do we get good data. So this is where all the analysis is happening, is in the middle of the mission. That's all of our data. That's it. That's what we got. Okay, it's actually a lot more detailed than this up close, because this is days and days and days, and yet we're getting 256 samples a second for all this. So you can see in the middle there, that's the strong part of the magnetic fields. The electric fields are well behaved as well. You can see at the beginning and end of the mission, the electric fields are getting kind of crazy. That's because of the bad illumination. On the right, this is the eclipse. We go into the dark and things go crazy. Magnetic fields have a little effect as well. So there's a lot to analyze that I'm going to scratch the surface on.
Why are there 3 traces instead of 4?
There's 3 components of the magnetic field.
Oh, that's what it is. I
Yeah.
thought it was in the 4 sensors.
No, the 4 sensors make the electric field. You take the difference. It's a difference of this way and a difference of this way. So you get X and Y electric, and then X, Y, and Z magnetic. Okay, so here I am working away on this into the summer, and I'm trying to do this magnetotelluric method. I had people that were signed up to do it, and it didn't work out. So I'm doing it myself, and I did not fully succeed. And along the way, I realized that the electrical conductivity of the surrounding plasma was like 10 times higher than I thought it was going to be. Plus, we put our magnetometer way away from the ground on this mast. So big mistake, which means that the signal fell off strongly with frequency. And so I can still save this. It can still be saved with smarter people than me who are now signed up to work on the actual magnetotelluric part. But in spite of the fact that this is called magnetotelluric sounder, I'm not going to do that right now. We went to the backup method, and that's called the magnetic transfer function. Okay, and this is not new. This is a way that you use something in orbit and you compare it at the surface. And it turns out you can you can derive the interior properties from that as well. This was done previously with Apollo 12, 1972, with an orbiting satellite. In our case, we have something called Themis, and there's two of them around the moon look like this. They got all these booms for electric and magnetic fields, and so we're able to compare what they were doing to what happened to our sensor at the surface. So I'm not going to show you any of the data analysis or anything, but just here's the answer. Oh, the side benefit of this is that, like I said, this was done for Apollo 12. So I can take that reduced data, the so-called transfer functions from Apollo 12, and analyze them in parallel with LMS. So I can reprocess in exactly the same way and make sure that I get that the approaches are fully consistent. So that ends up looking like this. So Apollo 12 is in red and Blue Ghost or LMS is in blue. And without going into the details of how I nipped and tucked, they're pretty close. And the thing I'm really interested in is the temperature difference. And so there's not much of a temperature difference except shallow. And how much is that? Well, it's less than 100 degrees. So from that site, Apollo 12, in the middle of what we think is supposed to be this hot spot of the moon, that temperature is less than 100 degrees hotter than outside where we landed. Okay, and that means that the cold models are the ones that can satisfy this observation. What does that mean for the moon? First, it means that the hotspot, so-called hotspot PKT, isn't today, and it never was significantly hotter than the rest of the moon. You can't start it hot and cool it down to be the same. It would still be hot today. That means that there were not enough of this creep, this heat-producing elements, just in this one region to make the main phase of basaltic volcanism. There's just there wasn't enough extra kind of packed in there. Well, how do we get the basaltic volcanism? It's not just there; it's everywhere on the moon, and that's just from radioactive heating. All planets have radioactive elements in the mantle. The Earth has lasted longer because it's bigger, but the moon went through a phase of volcanism. It just ended, 3 billion years ago, mostly. So I like to say arrested development of the moon. That means we still need a reason for why did it concentrate on the western near side. And this is a map of the thickness of the crust of the moon from a gravity mission. And it's very thin underneath the big impact basins, but this whole region, or PKT, has thinner crust. And this lets us invoke an idea that goes back to the 70s and 80s, really, that when the crust is thinner, it's easier for the lava to erupt, both because it's like less distance to get across, but also because of the hydrostatic pressure, it has to go to a lower elevation to get out. So it's kind of like a, So the western near side crust is thinner there and allows the eruptions to get out easier. So there's another angle to this, and that is a paper was published a couple of years ago where this group said, all of this thorium isn't necessarily being erupted with the lava and coming from, processes deep in the inside. It's just getting blasted out. So the idea is that this one big impact embryon, you can see how it's surrounded by this stuff and how it could have been thrown out around, and then it would have gotten mixed in with lavas over time. So the idea then is that the volcanism and the thorium, the creep, are both a consequence of thinner crust. So they're not genetically linked. So just proving what I said at the very beginning. And so why is there a man on the moon? Shorter answer is he leaked out through the thick crust. So what does this mean for the moon? It means that we don't need any special explanation of the inside of the moon to get to this volcanism on the western near side. There wasn't this concentration of heat-producing elements like we talked about. There wasn't, this is a paper that says, well, there could have been a giant blob that shot up from deep and made it. Well, we don't need that. Can't prove it didn't happen. An idea that was in 2 papers a couple of years ago was that the impact that made this giant impact basin on the far side could have pushed all this stuff over to the near side. Well, maybe, but you don't need it. All you need is this thin crust. That though is where my work has to stop. I don't have the answer to that. Why is there this thin crust? One idea that's been around for a long time is that there was an even bigger impact basin. The moon was all formed from stuff accreted and then stuff hit it. Most of the impact record on the Earth is gone. It gets erased by our active geology. But on the moon, we might be seeing a vestige of this giant impact basin from over 4 billion years ago. It's still controversial. The shape of the outline might have had to change, but that's one idea. The other idea is that at the very end of that magma ocean, there's a bunch of stuff left that's actually dense. It's iron-rich minerals. Those dense minerals want to sink. And so this idea that the inside of the mantle may have overturned on the moon has been around a long time. Well, what if that did something like rip some of the crust with it and left this kind of thinner crust behind? I don't have the answer to that. Either way, we're, maybe this is a tautology, but the moon is simpler in that we don't need these complicated mechanisms on the inside of the moon to make the western near side volcanism, but it's also more complicated in that we're left with this new problem of why is the crust thin? So where does this all end up? Well, LMS did make the first lunar surface EM measurements, electromagnetic measurements, since Apollo. It's been 50 years. This was the first successful landing, first kind of these measurements. And we're not done yet. Like I said, we have to go back and look at the whole magnetotelluric thing over again. But we got a pretty good first result with the backup method. And that result is that the western near side, the man on the moon, is not hotter than its surroundings, in contrast to what the conventional wisdom is. And that both the volcanism and the radioactive elements are consequences of the thin crust. They're not genetically linked. They're not causally tied together. So yeah, I can say that I've only solved one problem to reveal another one, and sometimes that's the way science works. So what's going to happen next is that we're going to do a mission to the far side, this thing called Schrodinger Basin, and it looks like this. So that's where we're going to land. And there's been a very recent paper that has, using gravity, has proposed that the near side and the far side at depth are different, that the near side as a whole is hotter. And that would incorporate both of the regions that we talked about, could still be hotter than what's on the far side. And we'll be able to test that when we go to this next location. So that is it. Thank you. I think Leslie was up first.
If the near side is hotter, does that make it less dense, and does that move the center of mass out from the center of body?
Center mass, center figure offset is like a kilometer.
Okay.
So it's just hard to pick up. They did this with time dependent gravity. They use basically the flexing of the moon on a monthly scale to say that the shear modulus was different from the near side and far side. Alan?
Yeah. What's the difference in the instrumentation you're applying Schrodinger versus crystal?
So we actually teamed up with the heat flow probe to form our suite. And so their heat flow probe is the same. I didn't show any of it, but it was pretty spectacular. Got a good result too. We are actually only flying our electric field system because there's another instrument that was already listed before anybody else got on. That's going to measure magnetic fields, but we're fully cooperating with them. So they actually get better magnetic field measurements than we would have done from a lower height as well. So we're teamed up with them to make a better measurement even on the far
The
side.
electric field hardware is the same.
Exactly the same.
When you were talking about the formation of the moon, when this big object crashed into the Earth, was there mixing? And so are the moon and the Earth essentially the same composition of material?
The core of the Mars-sized object merged with our core. The part that the moon got was basically our mantle. So the moon is very poor in iron, is one of the main leading ways that this theory is thought. So yeah, the moon is made of a mix of the two bodies, but only from their mantles. John?
Yeah, so in the next decade or so, between SpaceX and Blue Origin, both working on some much larger heavy lift landers compared to Blue Ghost. If we end up with the ability to put really heavy metal payloads on the moon, is that something your research would benefit from, or what's your dream experiment?
Yeah, I mean, everybody wants more mass, right?
Yeah.
So yeah, there's already been a couple of selections to go with the early Artemis landers, but they're still pretty minimal. People have studied, yeah, I mean, how would you in place entire networks of sensors? How would you have long distance, big vehicles that could travel a long way and do both surface and subsurface experiments? So yeah, I think it really just depends on the willpower for us to sustain a lunar program that deep to see that dream realized. Yes.
You mentioned earlier on in the talk, magnetic anomalies that you're trying to avoid.
Yes.
Actually, it's all the same, like, substance, but I was curious if you could talk more about like what.
Sure. So on Earth, like part of the reason plate tectonics was discovered is because the mid-ocean ridges the crust is spreading apart, but it's magnetized because of the Earth's magnetic field. So you get these stripes as the plates have spread apart, and you can actually reconstruct how the plates have spread. On the moon, when different bodies cooled back when the moon had a magnetic field, it froze in that magnetic field, but it's very spotty. It's not uniform, kind of like these big areas on the Earth. So something happened during the period probably when the lava was being emplaced in this former big hole in the ground from an impact. The lava was being emplaced in it, and there was some body that had more magnetic minerals in it, and so when the moon had a magnetic field then, and it would freeze in. We wanted to avoid that because just because the magnetometer can record that, but we'd like it to just kind of be near zero to get better signal. And also the magnetic fields can make plasma particles spiral and do kind of crazy stuff. There's a mission going this year. The next one that's going to fly is going to land smack on the giant magnetic anomaly on the western part of the moon. They're going to have a little rover drive out. They're going to investigate. There's differences in color of the surface because of how the magnetic fields interact. So there's going to be a lot more on that happening in the coming year.
Mark, so when we get major solar storms, can you pick that up with your instruments?
Sure. Yeah, I mean, we don't measure any plasma itself, but yeah, I mean, these data are about to be released publicly, and I would hope that space physicists and solar physicists, want to look at it because at least for a lunar day, we had an observatory on the moon that went through most of the environments. I don't think there were no CMEs or anything like that during the mission, but a long-lived experiment would certainly be able to record that kind of stuff.
Any other questions here?
Zoom.
How about the Zippers? You got any questions? Anybody?
Don't see anyone raising their hand. I think they can unmute themselves if they want to.
Yeah, if Zoomers have a question, you need to unmute yourself and then just shout it out. You must have just answered every question they would have had. Okay, say Barb.
I've answered this, but that thickness of the crust, is that the same on our side as the far side?
No, it's much thicker on the far side.
That's what I thought.
But the thickest part of the far side does not correspond to that patch of where it's kind of square. That's a thing all by itself. The PKT, the thin crust there, is a distinct low thin crust that's different from just the overall near side far side asymmetry.
Speaking of that, you mentioned that gravity might play some kind of role in that. Or is that referring to like tidal effects with it being tidally locked towards us? So our gravity on the Earth is, I guess, pulling more of that heavy material towards us?
that's an idea that's been around. In this case, they're just talking about that. Yeah, the moon has a bulge, kind of a permanent bulge towards the Earth. Now, of course, the moon, just because we're facing, the same place, the moon is still, revolving around us around the sun, and so they can see how over the monthly period how the moon actually flexes a little bit, and that's what went into this asymmetry. I don't know if that was your question or was it more general.
Yeah. I was just wondering if that
Okay.
was what we're referring to.
Yeah. It's tides. We have big tides in the oceans, but the moon also raises a solid body tide on the Earth, and then the Earth raises a solid body tide on the moon. It's small, but measurable.
Will you continue to get information from?
No, it's dead.
No, it's.
Yeah. Yeah, so these initial missions are not designed, so the lunar day is 2 weeks, lunar night's 2 weeks. And so these missions are only designed to last the 14 days of one day. We did we said goodbye, we took apart our ops center, we were done, and then we get this call, well, they're gonna try to wake it up. So, we all kind of remobilized, got everything set up again and waited around and, it never phoned home again. So that was it. As the next mission that I'm on too is only one lunar day, but the ones that are being competed now, NASA's starting to offer a service to last the night. So you can't really do a whole lot yet because you got to run on batteries the whole time, but it's going to evolve to where the real thing is that we don't send nuclear power sources to the moon yet, right? Everything we're doing is solar and battery. Back during Apollo, they just sent a little stick that was radioactive and it kept everything going for years. But we haven't kind of gotten back to that point yet. But yeah, so they will last, but ours didn't. Okay.
Anything else? All right, well, thank you, Bob. It is presentation.
So I can just close up, I've disconnected and it's clear.
Now I'm unmuted. How about John? Can you hear me?
Yep. Yes, I can hear you.
Okay. Turn that down. All right. Share the screen.
So the Mari are just lava flows.
Sure.
Mostly
Hold on,
they
let me
fill
check.
little spots in the ground, which are mostly impact. So the
Turned
impact
off.
bases up first,
Okay,
and the Mari.
okay, thanks. And, the formation of Turkey is a thing from the which is.
So the
Okay. That's working.
Okay, I'll be quick.
Let me make sure I'm safe.
Okay, we're safe, we're quick,
All right, we're good.
we're
Go
good.
to it, Leonard.
Okay, well, thanks. I write a lot about space exploration for space.com and some other places, and I tell you, I was like almost 13 years old today. It's pretty exciting for me. I'm getting older, but you know, living through the Apollo programs and even Mercury and Gemini space programs, and then into Apollo and lunar landings, and all of a sudden, you know, we're in a new kind of era with NASA. It kind of kick-started here just a few weeks ago with the new NASA administrator. This guy's flown already twice into space on his own dime. He's an entrepreneur, but he's been selected by Trump on 2 occasions. The first time it didn't go. Second time he submitted his name, and Jared Isaacman is now the NASA administrator. Pretty interesting guy to listen to right now. In my view, you know, I'm trying to be a negative reporter, but you know, NASA is sort of like the Exxon Valdez. You're not sure how you're going to steer this damn thing. And he's got a lot of interesting ideas. Could be closing NASA centers. It could be cutting off certain projects that he doesn't think are worthwhile. We don't know yet how this guy is really going to act. But he was good today. I must admit, he was a really influential speaker, because they rolled out this morning at about 7 o'clock Florida time the Artemis 2 mission, which is the space launch system built by NASA, and on top of that is the Orion capsule built by Lockheed Martin down the road. On top of that is an escape tower in case all hell breaks loose. So, you know, we got, for the first time in 52 or 3 years, people getting ready to go to the moon. This is not going to be a landing mission. It's going to be a circumlunar, kind of a figure 8 around the moon and come back. It's a 10-day voyage. These are the 4 Artemis astronauts that will ride that vehicle. And, you know, it really is an exciting time for NASA, even though the critics, you know, everybody is, you know, how much money is it going to cost? It's so expensive. But anyway, I think, you know, the euphoria around what's going on today was just reminiscent when I was younger of Apollo, and, you know, can we do it? Where are we going to go next? Jared Isaacman, the new NASA administrator, he talked about Artemis 2, but he also talked about Artemis 100, because he's got a big plan that the administration is now buying into. And, you know, we're going to see a lot of different kind of Artemis missions go to the moon, including landing, going to different places on the moon, eventually a long-term settlement, some kind of base. But we're not alone in putting that idea out there, and I'll get to that in a second. But it was a pretty exciting time here. This is all, I took this morning from screenshots, but these are the 4 Artemis astronauts with Jared Isaacman and public affairs person, a lot of people taking pictures, and these guys are headed for a 10-day voyage, and it's really a shakeout mission. I mean, Orion, nobody's ever ridden on the space launch system, so you've got, for the first time, humans on top of the thing, inside a capsule that hasn't been flown in space. There's a brand new kind of environmental systems and all kinds of other equipment on there that are going to have to be shaken out in low Earth orbit before they commit to go circumlunar around the moon. So it's not a slam dunk by any stretch of the imagination. And frankly, the astronauts today talking about the mission were really pretty candid about all the things that can go wrong. I mean, they've been practicing for a couple of years now as a team to really try to circumnavigate problems as well as going on around the moon. So it was kind of an interesting day today. When you really look inside the Orion capsule, here's the 4 of them in a practice session sitting in this thing. It's small. I mean, it's not a giant spaceship by any imagination, but this is the best we have to offer now for putting people out toward the moon. So very interesting collection of people and hardware that'll be shaken out. This is kind of an animation of going to around the far side of the moon, and I think I wrote down something here. It was pretty impressive. Yeah, 10-day voyage. Okay, the trip will take them as far as 4,800 miles beyond the lunar far side, and that is the most distant any humans have ever gone. So this is a very unique flight, and again, it just harkens back to the decades and decades ago of Apollo and the kind of excitement of those missions. If they're lucky and they take off on a certain day and a certain time and the trajectory is the way it's supposed to go, they probably for the first time, well, they will for the first time see the far side of the moon, and nobody has even ever laid eyes on that property by humans. We've had a lot of lunar orbiters and stuff that have taken good images of the surface, but for this particular mission, these people will be seeing something that no other human being has really imaged and looked at face on face with the moon. And there's a story I wrote for space.com. I had to do a whole thing about what are they going to do when they're on the far side of the moon. They got a giant Nikon camera, and they'll be taking pictures. And they're going to use tablets and all kinds of things. They're going to describe what they see. It's pretty interesting, and they've had short courses with professional lunar geologists. I mean, they're all honed up after 2 years to know what they're trying to look for and take best pictures they can. And also with the human eye, they're looking for all kinds of other activity that may happen in real time. One of them is an interesting possibility of actually seeing a meteorite hit the surface of the moon. You actually have an impact flash. So they're going to be looking for potential new impact craters. And anyway, it's really a pretty exciting time for plotting this out. Now, okay, yeah.
During the Apollo landings, didn't the command module orbit the moon?
Swing around, but yet the way I get it, the way they're coming in, they're going to be going in a different kind of trajectory, so they'll be seeing a lot of the far side that has not been seen previously.
Apollo landings on the near side had to be in daylight.
Yeah.
So when the Apollo missions were going, the far side was in darkness.
There we go.
Okay.
So it's really interesting, and we got a question here, I think, from somebody about, one bad thing about going to the moon is you actually have to land there. If you're really going to land on the moon, you have to have a lander. Well, we're right in the middle of a lot of discussion about these two particular characters, Elon Musk and Jeff Bezos. They both have different approaches for a lunar a lander that they're providing to NASA, or would provide to NASA. And today, Jared was saying he's briefed with these people, and both groups have an accelerated plan to land on the moon because of China. And this is becoming a potential, and it has been and is now, a space kind of race like the old days in the 60s. But we'll see where these people go. didn't have a lot of detail about how accelerated these plans are and what that would mean for a future human landing by the United States on the moon. Okay. But here's, on one side is Elon Musk with the big starship, and then on the other side is the Blue Origin concept. So we'll see. This is we have a space race, within our own country. Never mind China, and that leads me to what China is doing. They're moving forward. They have a whole multi-element program for returning to the moon with humans before the U.S. Depending on the date and time and all this stuff. But, they're looking at 2030, although there is rumblings now that things are actually coming together, and would they be in a position to even launch a human crew to the moon earlier than 2030. Bob did a great job on talking about the U.S. capability and how we're using robotic spacecraft. So too does China. The next mission will be this year at probably November, December sometime. They have Chang'e 7. It's a lander. It's going to the South Pole. It's going to land near Shackleton Crater. It has a little hopper. It has a rover. It is pretty well instrumented by an international payload, including a U.S. payload, a camera system that a friend of mine in Hawaii has put together, and it's on there. So they have a very active lunar lander program robotically. Chang'e 7 will be followed by Chang'e 8 in a couple of years after this year. And what they're trying to do is understand the area enough to set up a lunar base. So they're headed in the same direction we are. It's just the timing of everything and who's going to go first and who's going to be where and what they're going to do. Diplomatically, it's pretty interesting because one would hope we might work together, but right now that doesn't look very feasible. But who knows? So this is the landing area for the Chinese spacecraft that will touch down late this year near Shackleton Crater. And the thing about the Shackleton Crater is kind of an interesting place because it's one of those areas on the moon. You're trying to find a place that has potential water ice, and everybody's all excited about water ice and the craters that don't get much any sun. And can you use that water ice to make oxygen, water for drinking, rocket propellant, hydrogen, oxygen? Who knows? We don't know enough about what is there, how it's laying there, how to process it. But all this is all set up in the United States for what they call the human, to Mars mission. The National Academy of Science just a couple of weeks ago put out a pretty heady report about how what is the science behind humans to Mars. And as always, as you would guess, one of the leading priority is still, is there life on Mars? Was it there? Is it there now? Never had life. And so that's kind of a slam dunk there as priority one. But anyway, they had a pretty aggressive program of human exploration of Mars. So who knows where all this is going? Meanwhile, we got a rover on Mars right now that was collecting samples, and it is still collecting samples of Jezero Crater, where it's running around after several years now. And the point was, in our NASA budget, there was somewhat a turmoil because the expense of returning robotically samples from Mars was too cost prohibitive, and the timing was way out there, and a very confused picture, and it's still confused. of whether or not we're gonna go ever to this place with a robotic mission and collect the samples that have been deposited by the Perseverance rover, NASA's rover on Mars. And so it definitely has already asked this. It's found things already that people are very excited about. They can tell from the instruments on the rover that we may have found evidence of past life on Mars. Now, whether that's be the situation or not after they bring these samples back and really dive into them, who knows? But anyway, it's there running around. Hopefully it'll last for many years more, and maybe there will be a Mars sample return. Could be China will go pick them up. I don't know. Somebody will go. Anyway, I think that's about it for me. But I think today was it was a little bit emotional for me because somebody that's gone through all this human space flight. When you really start, you see the big rocket, the machine, and then you got 4 people that are going to ride this thing. And that's when it gets unnerving because we've never had anything quite this much of a milestone. And like I said, since the Saturn program and the Apollo program, the last flight was Jack Schmitt and Eugene Cernan to land on the moon in December of 1972. Wow. Somebody brought up a good point that we only have like 4 Apollo astronauts that are, I think, still alive, 4 or 5, and we had 12 people walk on the moon. So we're, our moonwalking, army is slowly dissipating. So NASA's going to have to catch up here, and Artemis 2 is the beginning of one wonders if a long saga. It could take off in February. Pretty doubtful. They rolled out the vehicle this morning. They plugged it in just as we came over here. It made it to the launch pad. It's sitting there. They're starting to plug in stuff and see, what the condition of the whole system is going to be like. And they're going to go through a wet rehearsal, what they call, putting liquid hydrogen and oxygen in the vehicle, and they're going to take it down to a few seconds before liftoff. There won't be an astronaut in there, but they'll do a test, and that's probably going to be the one where everybody goes, well, that's not working right. So you don't know about February 6th is what they're shooting for right now, maybe. So we'll see. But windows are opening in March, and, late in February, March, April. They got windows to launch these people. But we're back in the moon race. It's kind of exciting time. Thank you.
Any questions for Leonard? There you go.
Yeah.
Are there any other, big contenders in the moon race other than Chinese and American teams?
Well, the Indians have a really impressive program. They have a kind of a lunar landing program as well. Russia, I keep writing this in articles, but the editors keep taking it out. I'm kind of convinced Russia's coming back, and I think they're going to be pretty aggressive. They're working with China actually on the lunar base that China wants to set up. But Russia also has a lunar orbiter they want to put around the moon. They've had some bad, they were pioneers in lunar exploration early and did a lot of really incredible things with rovers and some other things, and bringing samples back from the moon. And, again, that's 50, 60 years ago. And a lot of those people that worked on those programs are gone. They're dead. Or and they got a younger crowd coming in, and they're making mistakes, and things are blowing up here and there. So, but I keep thinking Russia's going to be an active ingredient in the future. But you're right. There's other countries beyond China and the United States. So it's and then you just, you kind of hope maybe everybody can work together. Maybe not, but there's got to be some scientific sharing because, we're going to different locations on the moon and it'd be kind of fun to, have an exchange program. Yeah.
So, the Artemis rocket, is that kind of the same lift capability as the Saturn V?
I don't remember all the numbers, but I think it's not as powerful as Saturn V. I think Saturn V still holds kind of a record there, I think. But you don't want to stand near it when it goes. That's all I know. It's going to be loud. It's pretty impressive what they've done. They've used a lot of shuttle engines in the core of the Artemis to try to use those, and giant strap-on solid rocket motors. So it's going to be, to ride that thing. And, that's when you put the humans in there. Every astronaut that I've ever talked to, and I've talked to a lot of Apollo astronauts, when they rode the Saturn V, I mean, they do a lot of simulations, but once you're in there and it takes off, the rattling and what goes on inside this vehicle as it's going through the, atmosphere, it's a real hard, kind of terror grip. You can't even read the instrument panel; it's vibrating so much. So who knows what the Artemis astronauts will go through? But they were pretty honest about it. They trained for, I guess it's going on 2 years for this particular mission, and they know things are going to go wrong. They're just not going to be 100% smooth sailing, and so they've trained for all these incidents and whatever's going to happen. So yeah.
Question in the back.
Any more information on the health issue that cut the crew from the space station, that mission short? Did they publish anything else about that?
Well, I watched them get out. They came down, the thing flew over LA, and people saw the SpaceX Dragon bringing back the astronauts, and it was pretty cool. I mean, they landed off of San Diego. And I'm thinking, are they going to actually show the people getting off? Because then somebody's really sick. They looked all healthy. They're all going thumbs up, and I'm okay. So I don't know. We don't know. I think the only thing, in fact, they went to Johnson Space Center today and do more medical tests. So they're really, all reporters are trying to grind in, trying to think, okay, which person was the worst, or sick, that cut the mission out a month ahead of time, right? So it was the first time that NASA has gone through that emergency bringing them down, and there is this medical, they have a whole protocol that they really make sure that the astronauts don't get their medical data in front of the public. It's a private doctor-patient relationship. So you don't know what person was sick. I know the Russians had the same, something happened with one of the cosmonauts they had to bring down early on. And I thought it was kidney stones. Which, you got a calcium, all kinds of calcium imbalances going in weightlessness, but this person got sick and they had to bring that person home. So I don't know. I don't have any answer. That's what I was trying to get to.
Anybody else?
Okay.
Any Zoomers or questions? All right, folks.
Okay,
I think
thanks for
that's a
listening.
wrap. So we're going to come up, get back here, we'll take a little picture, and then after that we will pack up the chairs and stuff.